Welcome to Physics 30 Prep Fast Track, Lesson 4-2, Hooke's Law. Robert Hooke discovered a relationship between the force acting on a spring and the distance a mass attached to the spring is displaced from equilibrium. The cart above is attached to two springs and is currently at the equilibrium position. This is where the cart would rest if the system had no energy. Now, as you pull the cart to the left or to the right, then of course you would be doing work on this cart, applying a force over a distance against the energy of the springs. You would be giving the springs elastic potential energy, and of course in order to give them energy you have to do work on them, and the work is equal to F times D. However, Hooke said that the force required to move the cart away from equilibrium does not stay the same, but increases as you move further from equilibrium. So only a small distance from equilibrium, you don't need much of a force to get out there. But to get further and further away from equilibrium requires more and more force. And so he said that the force is equal to Kx. K is the spring constant. What that means is, depending on the material that the spring is made of, some springs are easy to compress or stretch. Other springs are very difficult to stretch or compress. And what he's saying is that every spring has its own unique constant. And the spring constant is measured in newtons per meter. That is the newtons of force. How many newtons of force are required to stretch that spring 1 meter? And so the further you move from equilibrium, the greater the force that wants to move the cart back to equilibrium. This is called the restoring force. So if you take Hooke's law, F is equal to Kx, and combine it with Newton's second law, A is equal to net force over m, you can put the two together and get A, that is the acceleration, is equal to Kx over m. All right, so all we did was take this Kx and move it right there. All right, and so we end up with Kx over m, and of course the further you move from equilibrium, the greater the force, and therefore the greater the acceleration that will move the cart towards equilibrium. So if you stretch this particular spring, or this cart, right now it's at equilibrium. If you stretched it way out here and then had the cart sitting at this point, then as it moved back to equilibrium, it would have a greater acceleration than if you just moved it a little ways. So at maximum displacement, you will have maximum acceleration. Now as it goes through equilibrium, x will be equal to 0, and therefore the acceleration at equilibrium will be equal to 0 as well. So the acceleration depends on how far you are from the equilibrium position. If you're further away, you have a greater acceleration. If you're close or at equilibrium, you have 0 acceleration. But then, of course, you have lots of velocity at equilibrium, so therefore that velocity will carry you away from the equilibrium position, and therefore the force by the spring will actually want to accelerate you back, and it will slow the object down. So in order to move the cart a distance from equilibrium, you must exert a force, and which means you have to do work. And the work gives the system elastic potential energy, which of course when released will turn into kinetic energy. And so you have if this was an ideal system, you would have a trade-off between elastic potential and kinetic energy. And so the work you do is equal to Fd, and of course remember from Hooke's law we know that Fd is equal to, force is equal to Kx, and so Kx times d, d and x are the same unit, distance or displacement from equilibrium, and so we end up with Kx squared. Now we don't actually use work is equal to Kx squared, and the reason for that is that the K we're using in this equation is the maximum displacement, but remember that minimum displacement is 0. So the average displacement is not the work you do is the average displacement, which is d over 2, or that is maximum divided by 2. And so instead of having kx squared, it ends up being equal to 1/2 kx squared. And that's called the energy of a spring. And so it's similar to 1/2 mv squared, but is the elastic potential energy of any spring. And that includes any other type of spring system, such as an elastic band or a bow and arrow. All are examples of elastic spring systems. So the work you do on a bow and arrow is 1/2 kx squared as well. You'd have to just know what the k value is for that system. So when a card is released, the system oscillates between potential and kinetic energy, speeding up and slowing down until friction brings the system to a stop. If this were an ideal system where there was absolutely no friction, then this system would have the ability to oscillate back and forth forever.